Isaac Newton. I don't profess to know what a genius actually is, but whatever the definition is, I think he was it. He and Leibniz both independently developed calculus. Any person that develops calculus, like from nothing, has got to be a bit freaky. When it comes to motion, he's got laws and he's got equations. Okay, so let's look at the laws. And there's basically three laws. They're called Newton's laws of motion. And personally, I think it's slightly misnamed because I think they should be laws of forces or of force, because they're all about force. They're not about motion. Two of them are, but the third one isn't. The first law is all about balanced forces. If the forces on an object are balanced, so I'm going to pause there for a moment. Dogs have them. Paws. Do you get it? Dogs have them. They have paws. If the forces on an object are balanced, that means they add up to produce a total force equal to zero. Cancel out, in other words. If the forces on an object are balanced, the object will not accelerate. Now let me say that again. If the forces on an object are balanced, the object will not change its velocity. That means the same. Acceleration means to speed up, to slow down, or to change direction. I'll say it again. If the forces on an object are balanced, the object will continue at constant speed in a constant direction. That's the same as saying a constant velocity. Now those are the three different ways that you can say the first law. And the one I like is if the forces on an object are balanced, the object will not accelerate. I prefer that one, but almost nobody says it like that. It's just more concise. Balanced forces lead to an acceleration equal to zero. That's the same as saying that delta V is zero. That's the same as saying, flipping heck, V is a constant, including zero. Zero counts as a value. So in other words, an object can be stationary and it will stay stationary. It could be moving at 1 meter per second in that direction, and it carries on moving in 1 meter per second in that direction. This is in contradiction to Aristotle. Those Greeks get everywhere. Aristotle thought that the natural tendency of an object was to be on the ground and stationary. And that's because everything around him seemed to be on the ground and stationary. But this is incorrect. Aristotle thought in order for an object to be moving, there has to be a force acting on it. Because again, when he looked around him, that's all that seemed to happen. Objects move when they were pushed. If you stop pushing them, they came to a halt. They stopped. And that's because of friction, of course. Aristotle was surrounded, like we are, by a world of friction. And it looks like, you know, everything like comes to rest if you leave it alone. Okay, so that's the first one. The first one is about balanced forces. The second law is about unbalanced forces. And it tells you what happens to an object when the forces on it are unbalanced. In other words, they don't add up to zero, they add up to a non-zero value. If the forces on an object are unbalanced, the object will accelerate. Acceleration not equal to zero. And that means, of course, that delta V is not zero, and that means that the velocity is changing. I kind of warn you now, if you hear dogs bark, I've got 3 dogs, 2 little Jack Russells and a beast. You'll hear the beast because it's like this deep, deep voice. So if you hear them, we have to ignore them. Okay, so that's unbalanced forces. Now, you could be forgiven for saying, yeah, okay, laws of motion seem about right because it's talking about motion. But it's the third one that messes that up. The third one is about forces in pairs. It's got nothing to do with motion. For every force, there's an equal but opposite force. It used to be for every action, there's an equal and opposite reaction. I remember asking my teacher at the time, what does the word action and reaction mean? And he just said, oh, it just means a force. It is probably the most misunderstood of the 3 laws, and it's nothing to do with motion. And we're not going to delve into this in much detail. Very often in physics, we're lazy with the words. We say things like, the moment of a force is the force times the distance, or the force times the distance from the pivot point. Work done is force times distance. For every force, there's an equal and opposite force. In all of those 3 sentences, we've shortened the sentence because we can't be bothered to give the full sentence. So for example, the moment or the turning force is the force times the distance from the pivot. That's not true. It's the moment is the force multiplied by the perpendicular distance from the turning point or the pivot. And that word is really important there. Okay, work done is force times distance. That is not correct. Work done has 2 definitions. One to do with mechanics, another one to do with energy. The definition here is the work done on an object is the force multiplied by the distance travelled in the direction of the force. And that last bit is really important if you're going to understand it properly. This one, forces in pairs. For every force there's an equal opposite force. Again, shortening of the sentence. It should be something like, wait for it because this is going to be horrendous. For every force there is an equal but opposite force, and the equal but opposite force is not acting on the same object. We should also say it's of the same type. The equal but opposite force is of the same type but not acting on the same object. I've got a yellow pen here. What are the forces acting on it? Now at the moment there are 2 forces acting on it. There's a force down from gravity and there's a force kind of upwards resisting it from me. Those 2 forces, the reaction force from my hand and the gravitational force, they are not what Newton's talking about. If you look at any object and write down what are the actual forces acting on the object, then for every one of those actual forces there is an equal but opposite force. So for example, I could say there is a force of gravity on the pen from the earth. The equal but opposite force, there's a force of gravity on the earth from the pen. So in other words, the earth pulls the pen down, the pen pulls the earth up. That's the equal but opposite force. There is a reaction force on the pen from my hand. There is a reaction force on my hand from the pen. If you write down the sentence, there is a gravitational force on the pen from the earth, and what you do is you just flip those 2 names at the end. There is a gravitational force on the pen from the earth, on the earth from the pen. Flip them around. That's the equal but opposite force. What I'd like to do is I'd like to just focus on the second law just for a moment. So let me just separate here. Newton actually said if the forces on an object are unbalanced, in other words, you add them all up to get F total. If the forces on an object are unbalanced, it will cause it to accelerate. What he actually said was this: the total force is equal to the rate of change. That means with respect to time. The word rate means per unit time of momentum. Momentum has the symbol little p. In any change, the change is the final value minus the initial value. So that means that's p final minus p initial over delta t. That's going to be mv minus mu. Now I'm using the Suvat idea of final is a v and initial is a u over delta t. And that's going to be m, and I'm really dredging this out, v minus u all over delta t. And of course that bit is a. So F total is ma. And that's where that equation comes from. Probably the most important equation in physics, although if someone was talking to me with a physics degree they'd probably pick a different one. Please note, it's really important, F total is the total force, it is not an individual force. If there is only one force acting on an object, then F total obviously is that one force because there's only one. That would be an object, for example, falling with no friction. If there are 2 forces acting, you have to add those 2 forces up, and don't forget they're a vector. If it's 3, then again you add them all up, and that is F total. F total is not a specific force, it's any forces added up.